Now we start with the thin film growth and nucleation, or nucleation and film growth mechanisms. So nucleation and film growth mechanisms, they actually mainly have four parts, which will have it is the condensation of the film, coalescence of the film, and nucleation of the film, and then accordingly the growth of the film. So if we write down these main parts, so the main parts are condensation of the film, next is coalescence, next is nucleation, and growth. So these are the main parameters which actually thin film growth and nucleation they have and they are concerned about. So primarily the thin film growth condensation is actually the condensing particles which are being actually condensing on the substrate surface, and then accordingly they merge together to have the coalescence, and then they nucleate together, and then accordingly the growth will take place. So the growth of thin films from gas phase is a non-equilibrium phenomena governed by the competition between the kinetics and thermodynamics of the material particles. So there are three stages which can be distinguished in the nucleation and growth thin films. So we can say that these three stages are stages of thin film growth. So these stages are the production of ionic, molecular or atomic species in the gas phase, production of ionic, molecular or atomic species. So this production of ionic, molecular, or ionic species, they are basically concerned about the particles before the deposition on the substrate, and these are concerned about the thermodynamics, which contains the state variables, laws of thermodynamics, Gibbs free energy specifically, along with the temperature, pressure, and volume variations. So if we change these state variables and according to the thermodynamics of the material particle, then accordingly its deposition, its condensation on the substrate will be changed. And then if it is being changed, then accordingly it will change the surface morphology or the growth mechanism of the thin films. So we have to be very careful about the consideration of these thermodynamic parameters, like the ambience of the material particle in which we are depositing it on the substrate surface. So the second one parameter is the transport of these species to the substrate through a carrier medium. So means that transport of species to the substrate. So if we transport these species to the substrate and accordingly we change the pressure of the ambience, then accordingly its energy will be changed, and if its energy is changed, then accordingly its condensation and all the parameters, rest of the parameters will be changed. So if, for example, if we change the pressure, if pressure is higher, then accordingly it will have more collisional effect with the ambience and it will lose energy, its kinetic energy, and accordingly its temperature will decrease, and which will result in a change in enthalpy and gives free energy of the particle. The next one is the condensation of the species onto the substrate. So it's the third stage. Condensation of species to the substrate. So these are actually the three stages in which a particle being produced and then accordingly transported to the substrate surface, and after the condensation the rest of the mechanisms or the thin film growth, they are started. So for the those parameters for which in the thin film growth actually is being initiated, they can be discussed in this diagram, which contain the basic phenomena for thin film growth. It's a substrate surface on which the material particles are being deposited. So a material particle is actually coming up from this ambience and it deposit on this substrate. So before the deposition, all this phase before deposition is concerned about the thermodynamics, dynamics of the particle. So these thermodynamic concerned about that, as we have already discussed about the state variables, which include the laws of thermodynamics, temperature, pressure, and entropy, energy, Gibbs free energy specifically, which can affect the deposition. So this particle is depositing on the substrate surface. So it's direct deposition on the substrate surface. So this particle is deposition on substrate. So one possibility is the deposition of this particle on this substrate. The other possibility is the deposition of the particle on the cluster. So meaning that if the particle is over here, it's directly actually depositing on the substrate. But there is another possibility that the particle, there are cluster formations. So clusters are like this, the atoms are joined together and formed the cluster. So this one is the cluster formation. After coalescence, the atoms, they form the cluster. So the second possibility is the deposition of this particle on the substrate surface, or on the cluster. So in this situation, the particle will be deposited on the cluster. So deposition on cluster. So there are two possibilities. The atoms, they actually deposit on the substrate surface or on the cluster formation. The other parameter is once they are being deposited, then they actually move on the substrate surface. So this movement is actually the diffusion of the particle to the cluster. So after the diffusion of the particle to the cluster, they diffuse together and form a cluster, and accordingly there is a possibility that they are material particles, they are deposited on the cluster. So if the temperature actually being higher, then there is a possibility that the particles will be re-evaporated. So another parameter which is concerned about the particles with higher energy, they can be re-evaporated. Re-evaporation. We can also call it as a desorption of the material, in which the particles they re-evaporate from the substrate. And the last parameter, which is the initial parameter for the nucleation, that the particles, the moving particles, they actually nucleate together. So this one is particle nucleation, in which they come together to nucleate. You can see that cluster nucleation. So in this situation, these basic phenomena related to the deposition of the particle on the substrate, diffusion of the particle to the cluster, the deposition of the particle on the cluster, and then cluster formation, nucleation, and re-evaporation. These actually are the basic parameters or basic mechanisms which are taking place while we are depositing the thin films or the materials on the substrate surface. So vapor atoms, they are continuously depositing on the surface. Depending on the atom's energy and the position at which it hits the surface, the impinging atom, the depositing atom, could re-evaporate from the surface to absorb it, so becoming an add atom. So in that situation, add atom, that phenomena are related to the adsorption actually of two types. So mean that adsorption can take place on the surface of the substrate either by van der Waals bond or by chemical bond. So if the adsorption is taking place on the van der Waals through the van der Waals bond, that adsorption is called as physisorption, and if it is forming a covalent bond with each other, then it is a chemisorption. When atoms are physisorbed, they can migrate on the surface and interact with each other as well as with the substrate atoms. So these interactions determine the morphology of the growing film. So the rate at which the atoms are adsorbed to the surface obeys the Arrhenius type of equation, which we have already discussed, that is equal to a VA exponential EA over KT. So this Arrhenius equation actually give us the information about the rate at which the atoms are being adsorbed, where EA is the adsorption energy, K is Boltzmann's constant, and T is the substrate temperature. So most substrate surfaces have complicated reconstructions, and the bonding is highly directional. Therefore, the probability of adsorption to some sites is higher than other.